Hello, everyone. Who did not have the tiramisu? You all you made the wrong decision. It was excellent. Actually, the food here has been pretty good all day and yesterday. So I'm absolutely stuffed. I hope you are too. But also that means you're probably going to fall asleep because it's the first after lunch session. So I'll try and keep it a little bit lively, a little bit engaged, so you don't fall asleep. If you do, totally fine. I fell asleep in my wife's talk just before lunch. Don't tell her I said that. So we'll see how it goes. So who am I? Who's this clown? Hi, my name's Ben. I've been coding for 12 years. No, I've been coding since I was 12. You can tell I haven't had enough coffee today. I've been coding since I was 12. 12 years is far too short. I feel much older than that. I've been breaking software since I was 15. I've loved security, privacy, and then the adjunct things like civil liberties and all of those kind of things for quite a long time. I've been running tech events, so I absolutely appreciate what it takes to put something like this together. So for those few actual crew members in the room, thank you so much for everything you've done. I successfully set my hair on fire at a tech festival when I was 40, so don't trust everything I say. I'm not necessarily the best adult in the room. If you want to contact me, I'm on Blue Sky at Ben Dechrai with the dot in the weird thing. So that's about me. What I want to talk to you about today, security, encryption, how to encrypt things, what kind of encryption algorithms there are, how they work, when you should choose them, when you shouldn't choose them, all of those kind of things. But we'll start at the beginning. There are three things that are certain in life. Does anybody know this quote? It's not the one you think. Phishing, data theft, and, because it's topical, authoritarianism. And these are the kind of things that we face day to day as software engineers while we try and keep our users safe and our data, their data, safe. So why do we need encryption? There are a couple of reasons why we might want to encrypt things. We might be enforced to because there are regulatory requirements for us to do it. Especially if you're doing stuff in Europe, you'll be familiar with the GDPR. There are plenty of other regulatory requirements for you to keep your users' data safe. There's also a bit of a clash there as well, because GDPR and some of the others also have a right to be forgotten. So how you store things, how long you remember them, whether you're allowed to remember them, whether you're allowed to not forget them. Double negatives, hate them. But some examples here of why you might want to do this. In 2021, Colonial Pipeline paid $4.4 million in ransom after an encryption attack. So they had their data encrypted and then ransomed. You've probably heard of these stories. $4.4 million later, they got their data back. Company reputation, PR at risk. That obviously affected them in some ways. GDPR fines can reach $20 million euros. It's probably about the same. My maths isn't that great. Or 4% of your global revenue. So if you earn shitloads, you pay shitloads if you get caught. Other reasons, user trust and expectations. So Uber, for example, paid a $100,000 ransom after a data breach and then tried to hide it. I don't feel that really leads to a lot of trust for users. And Signal user base grew by 4,000% after the WhatsApp privacy changes. That was so excellent. It's back. Heather was having issues with the screen flickering during her talk, which apparently is down to maybe having done live demos, but given that I'm nowhere near it at the moment, I'm putting it down to the ghost in the machine. We'll see how this goes on. We also have a couple of live demos, so jiggery-pokery on the laptop could create issues, but we'll see. We'll be fine. So what we're going to do today is we're going to build a chat app. Has anybody ever built a chat app before? Simple data from one person to another into a database? Half of you. The other half are probably lying. It's not that, maybe you're not lying. It's not that different to the standard, like, write a blog in 5 minutes. I don't think you write blog, but you know, probably one of the simplest things you can do is have an input field, put some data into it, save it to a database, and display it on another screen. And we'll go through some demos, and we'll build it up piece by piece, and learn what kind of encryption we can use to protect the data. Now, this will extend beyond just chat apps. No matter what data you're storing, what kind of business solutions you provide, everything is about data in, data out. And how do you store it in the middle? How do you store it in transit? How do you keep that data safe? Will apply to a chat app as much as it will probably most of the problems that you'll be facing where you've got to consider that security aspect too. So, simple chat app, I've kind of already described it, but let's go with some icons anyway because they're fun. So we've got Alice and Bob. In a typical encryption story, you have a number of users, and the standard ones are Alice and Bob. They're always trying to communicate secretly with each other. You'll meet Eve later. Eve is the eavesdropper. Charlie is the third participant. So Alice and Bob start out a conversation, and Alice basically wants to say, hi. So Alice writes hi into the chat app, sends that to the server. Server stores the plain text hi, sends that to Bob. Bob can read the message. Excellent. And then we have a demo. Excellent. Let me see if I can switch over. All right, so we've got two chat apps here. They're the same app. We've got 4 different users. So I can switch between any of them if the mouse will work. There we go. We've got Alice, Bob, Charlie, and Eve. I'm not quite sure if that's totally readable at the back there. Can you see the small print? Excellent. So we've got Alice, Bob, Charlie, and Eve who can all take part in different conversations. And we've got some existing conversations set up already. So we're going to jump into the chat here for Alice. You'll also notice that as we go through, we have different colors so that we can kind of half remember whose device we're on. So we're on Alice's device at the moment, and Alice wants to send a message to Bob, and she's going to say hello. Meanwhile, if we go over to Bob's phone and we have a look in the chat message, you can see it's there. And you're like, well, that could have been there already. So, yo. Because Bob's down with it. Come on, demo. You can do it. There we go. Message arrives on Alice's machine. So, in order to kind of delve under the hood and see what's going on here, I built a little admin tool so that we can go in and see what's actually happening. So let's have a look in here. We can see we've got our users table. We've got Alice, Bob, Charlie, and Eve there, and their preferred phone colors. Very important information to store. We've got our conversation. So we've got a conversation between members 1 and 2. That'll be Alice and Bob, Alice and Charlie, Bob and Charlie, and then there's a group chat between all 3. You'll notice that Eve, the eavesdropper, is not a member of any of the chats yet, but we can change that. And then we've got the messages. And we can see down here quite plainly the content, hello and yo. So if somebody gets access to the database, we can read the data straight out. Which, for a simple chat app, is probably not the end of the world. So let's conclude with the problems we already know there are going to be and work out what the next step is. So we've got Eve comes along, and they're like, you know what, I want to find out what all the conversations are that are going on. So Eve is expert hacker, either got direct access to the server or maybe is able to make a request to the API endpoint to receive the messages out. And because they're plain text, with the exception of access control, which doesn't protect your data, it just stops people potentially from hitting certain endpoints, Eve is going to be able to get this information out. In fact, Eve plugs her laptop in, and there you go, she's got the message, so it says hi. So we want to make this a bit more secure, so let's encrypt it. Let's build an encrypted chat app. So we've got our starting position. Alice and Bob want to send a message. Alice sends a message to the server, stores it on the server. The server, meanwhile, has some kind of shared secret that it's aware of for symmetric encryption. So symmetric encryption is where you can encrypt data with a key and use the same key for decrypting it. So it creates some kind of, there's an example piece of code here. It'll create an initialization vector. The initialization vector is essentially just this random starting point of information. And then it'll take the data that it wants to encrypt and uses the initialization vector to encrypt a block of that data. And then it uses that block of data as the next initialization vector to then encrypt the next block. Don't need to know how it works technically underneath, but essentially that's what's happening here. We're getting that initial initialization vector, the encrypted data, and then we're encoding the plain text and returning that to the database. And you can see down at the bottom there, we've got the 011M09URP, blah, blah, blah. That's the encrypted version of hi. You can see it's padded out really, really quickly all of a sudden. But we have the encrypted version on the server now, so technically anybody comes along and has a look at that, they don't know what it says. Meanwhile, Bob comes along and says, okay, do I have any new messages? And it makes a request to the server saying, send me any new messages. The message comes along, but before it does, the server will then use that key again, decrypt it, and here's the counter to that, how to decrypt some code. Again, you start with the data that comes in, and then you decode it and you pass the unencrypted version hi back out. So the server's decrypted it, got the word hi, hi gets sent to Bob. Server can then forget hi, can always decrypt it again later if it needs to. And Bob receives a message. Meanwhile, if Eve comes along and tries to access the data on the server, they're just going to get the encrypted version. However, there are two things that could happen here. Eve, if Eve has access to the server in order to read from the database, might also have access to the code and perhaps the environment variables and be able to find that one key. Alternatively, Eve could just, am I jumping ahead to another slide? Eve could just make a direct request to the endpoint. As I was saying before, Eve could connect to the server directly, or could make a request to the API. And if the API's access control is insufficient, the server's still going to decrypt that message in the same way as it did for Bob. So I believe that slide will probably come later, and I'll be totally surprised, as will you. So let's come in over here, and we're going to go over to demo 2, symmetric encryption demo. So if we come in and we open up Alice and Bob's conversation, we can see the hello and yo because, of course, they're plain text. And in this case, we're just outputting them anyway. But if I send another message and say, how are you doing? And Bob replies, not bad. There we go. Bit of a conversation going on. If we look in the database again now, we'll see under here that the content is now no longer plain text readable information. This is now the encrypted information we had. But let's say that Eve managed to get that decryption key. Don't photograph this either. The encryption key is super secret encryption key. Highly technical. And there you go, it's decrypted already. So you've got the how are you doing at the bottom there. So this message isn't particularly targeted at a single user. The decryption key does not belong to a particular user. It's just one decryption key. Every message can be decrypted with that one decryption key. And we'll come into key rotation later as well, which is one way of reducing the effect of a key being leaked. But it still has this problem when we look at symmetric encryption because of the fact that there's one key for everyone. Let's see. If we have a look here, we've got a get messages query endpoint. So if I come here and for conversation 1, make a request for that, we'll also see similarly that we've got the hello and the yo, but then down here we've got how you doing and not bad. So this is the response directly from the API endpoint. And because I don't have authentication on that API endpoint, the server's like, well, I'm just going to decrypt it because that's what my server-side script does. So at this point, we've got the data in unencrypted forms on the two devices, and it goes unencrypted to the server, and it only gets encrypted on the server. So in transit, it's still in plain text form. Probably not ideal. So, yeah, so this is the slide that I was talking about before, and as demonstrated just now with the accessing the API directly, if Eve then decides to make a request through the API, through a REST-based request rather than trying to get into the server itself, the information is still going to get decrypted because the server's endpoint is like, well, my job is to decrypt the information and send it out plain text. So that's how Eve can get into that. So what we're going to do now is do an end-to-end encrypted chat application, building upon the previous encryption. So now what we want to do is rather than have it plain text at either ends and then encrypted in the middle, we want to encrypt it at either ends, and then it doesn't matter what happens in the middle. Because now we're protecting it at rest on the server, but also in transit between the server and each of the endpoints. Endpoints as in chat app clients, not API endpoints. So how's this going to work? Alice and Bob, again, having a conversation. Alice is, first of all, going to generate a key pair. So to generate a key pair, you generate a random private key, and from that random private key, you can then derive a public key. And as it might sound, a private key is something you keep private, and a public key is something you keep public. How many people here have played with public-private key encryption already and mostly familiar with it? Okay, about half of you. So Alice now has this public key and a private key, and she will share the private key with Bob. Meanwhile, Bob generates a public and private key and shares his public key with Alice. Alice can now type a message in, but before it gets sent, is going to use Bob's public key to encrypt it. So public keys are always used for encrypting, and you encrypt it with a recipient's message. And private keys are always used for decrypting. We won't go into it in this, but as an aside, public keys can also be used for private keys can also be used for signing. So I can take a piece of data and use my private key that only I have access to and sign a document of some sort, whether it's text or whatever. And the signature of that can then be verified with my public key. So it allows me to use my public key in a way that changes the output. Private key in a way that changes the output, just so you can verify it's actually from me. So it's more of an identity assurance as opposed to encryption. You can also do both. So I could sign it with my private key, then I can encrypt it with your public key. You can then decrypt it with your private key and verify that the information actually came from me by verifying it with my public key. There's a bit of an inference in the fact that I encrypted it anyway, but the two can work together. So Alice encrypts with Bob's public key and then sends that over to the server. So the server only ever receives encrypted information. No matter what happens now, whoever gets access to that cannot decrypt it unless they have Bob's private key. So Bob makes a request for any new messages. This information comes over. It's totally scrambled, doesn't know what's happening. He will then, as I say, use his private key and apply that to the payload that came in, decrypt the information, get the original message out. Clear as mud? Excellent. So as I mentioned, Eve can come along. Absolutely nothing they can do in terms of decrypting the information on the server if they access it directly. And if they do it through the REST-based API, they're also going to get the encrypted data because we're not actually touching the data on the server anymore. Essentially, the server is now acting as the original server that we had, the plain text, because all it's doing is getting information, storing it, and then sending it on to somebody else. So we now have the advantage why they call it end-to-end encryption, because it's encrypted from end to end without any unencrypted version of it appearing outside of those two end devices. So this brings us on to the next demo. All right, demo 3, end-to-end encryption. So as I mentioned, each of them needs to generate a private key, public-private key pair. So we're going to do it for Alice first. And we won't do anything for Bob just yet, just to see how it works when keys are kind of in flux. We'll see here that we can't decrypt the message, because now our chat hub is basically trying to decrypt the message using that was encrypted on the server in symmetric encryption mode. But of course, the server isn't decrypting it anymore. In demo 3, the server is just taking data and pushing it back. So in fact, our app is now getting encrypted data. So it wasn't able to decrypt it. So we've got a private key pair, public-private key pair over here for Alice. We can see over here, here's Alice's public key. And we can see down at the bottom here, she has one key pair, public and private. Bob currently has no public or private key. So if we send a message over here, hey Bob, we'll see the message appear in our messages table, which is still in JSON. And in fact, in this version, we'll get onto this a little bit later. In this version, we're actually using we're still using shared key encryption, and I'll discuss why that's a better option. But in this case, we've got initialization vector and a payload still. If I copy that and paste it into this lovely JSON prettifier, we can see a bit more of what's going on. So we can see that sender 1, Alice, has sent a message to user 1. So here's the thing. If you want to send a message to somebody and you want to be able to read it again, you have to encrypt it for yourself too. Because otherwise you're encrypting it for Bob. Bob can decrypt it, but you can never decrypt it. Yeah. So Alice is encrypting it for herself. And then also, well, actually not encrypting it for Bob. Can anybody suggest why it hasn't been encrypted for Bob? It doesn't have a public-private key pair. So let's do that. Let's come over here. Let's move that over. And we'll come and we'll generate a key pair for Bob. So now we'll see that Bob has a public key. Now you'll notice that down at the bottom here, we've got this key management. So we've got a list of all Bob's keys, and we can see Bob now has a public-private key pair. Actually, we can't because the admin tool isn't refreshing properly. But I mean, it's in there. It's a bug in my admin tool. But so this is what is on Bob's device. But at the top there, we also have a list of just the public keys in the public keys table. And the reason why we have that is because when Alice wants to encrypt the message, Alice is going to go to the server and say, hey, I'm in conversation 1. Can I have a public key for every member of conversation 1 so I can encrypt it? So if you join a conversation, and we can add Charlie in and see how that works. If you join a conversation, then you need to let the server know what your public key is, public key is, in order for future messages to be encrypted for you. So let me just close the admin panel. And we'll come in here. So we'll see the message was not intended for you comes up because it was encrypted for Alice, but not for Bob. And yet it's showing up in the conversation. And the app's like, sorry, dude, I don't know how to help you. I don't have a version of this that you can decrypt with your private key. So Bob's going to be like, eh? And that goes through, but now it's being encrypted for both. Phil has a drinking problem in the front row here.
In this example, they're using both Bob and Alice are using the same code base of the same app, basically, right? Just
all the demos?
Bob and Alice
are
actually accessing the
Those are the same app with their two instances in the page. So they're, yeah, totally.
So what would be the difference if the app just has one pair, one master pair, and encrypts everything?
So if the app had one master pair across all devices?
Yeah.
Yeah, so one of the hard parts is, so the question is basically, we've got a public-private key pair for Alice and one for Bob. Why not just have one public-private key pair for the app? So the problem is that with that is, how do you distribute it? At the moment, we're generating the public-private key pair on the device, whereas if it was for the app, every instance of the app, you would have to somehow distribute that to every device that it gets installed on. And at that point, the private key is being transmitted somehow. Now, we'll actually talk about where you can do that securely later, which is useful for, anybody here use Signal? Anybody have Signal Desktop? Right, so to get Signal Desktop working requires a way for your mobile device and your desktop application to communicate with each other to share that identity. And they do it in a really interesting way. They don't actually share public-private keys. I won't go into that because I've got slides for that. But yes, the problem you have now is the distribution channel for getting private keys to these devices. The whole idea with public-private key encryption is that on the device that you're going to use for communication, that's where you generate them, and the private key should never leave that device. Good question, though.
In this case, the reason that Bob doesn't get Alice's is that Alice hasn't shared the public key with Bob.
So Alice has shared the public key with the server, and then when Alice wrote the first message, the server said, here's a public key for you to use to encrypt, which happened to be Alice's. But Bob didn't have a public-private key pair yet. Therefore, Alice wasn't able to encrypt it for Bob to be able to read. But then once we generated the public-private key pair for Bob, his public key was shared with the server. So then when Bob just sent the message now, which we can see on the screen,
Bob's public key would be different from what?
Bob's public key is going to be different from Alice's public key.
So Alice encrypted with her public key.
Yes, and only hers. And Bob is now encrypted with both.
Encrypted with his public key, not the Alice public key.
Both. So he would have made a request saying, give me all the public keys for people in conversation 1. So we can see in conversation 1, we've got two members 1 and 2. And then you can see under the public keys, the two users 1 and 2, there are two public keys. So the server would have given those two public keys to Bob. Bob would then use those to encrypt his response. And if we look in how that actually manifests, we can see it's actually created two payloads. So we've got the recipients array at the top, and in here we've got the first, I can't actually highlight this, we've got the first encryption, which is intended for user ID 1. We know that's Alice, so this was encrypted using Alice's public key. And we've got the initialization vector and the ciphertext in there. So now Alice can use her private key to decrypt that. Bob can't decrypt that one, though. But what the encryption process did was it also created a second message. This one is encrypted using Bob's private key. So now Bob can decrypt this one with his public, wrong way around. It encrypted with Bob's public key, and he can now use his private key to decrypt that message. So both of them receive both messages, and they try and decrypt all the messages. And Alice is like, I can decrypt that one, I'll show that. Bob's device goes, I can't decrypt that one. Oh, but I can decrypt that one, okay, I'll show that. So it just rotates through all of them. Now, we do have an ID in there as well, so they could look up and say, only find ones that are for me. But even if you didn't have that ID, which can be useful for anonymization purposes, you can just iterate through all of the messages and just show the ones you can decrypt. Is there a question?
So, scaling-wise, this would be problematic if you...
Oh, totally. I've got some great slides with lots of arrows coming up. You will like that one. All right. So let's just have a bit of fun here and see what happens when we add, let's add Charlie to this chat here. And now let's switch over to Charlie's phone. Now, Charlie doesn't have a key pair yet, but in any case, we know that none of these messages have been encrypted with her public-private key pair because they haven't existed until now. We can see that her public key is now in the public keys table. So next time a message comes in, it'll be encrypted with 3. And you can see here that none of these messages are intended for Charlie. The first 2 were plain text from demo 1. So let's, I'm here. So we can see now that Bob should be able to see that message. There we go. And we can see that Charlie has successfully registered in that channel. Their name is showing up there. We can see that these have been encrypted. These have been decrypted with Bob's key, CD8, and this one should also be CD8. And then Charlie over here has a new one. So Charlie is now able to converse in this channel as well. And as I mentioned before, because every encrypted version can only be decrypted by one public key and private key. I hate the fact they both begin with P. My brain always gets confused. If you use PGP encryption, and now I'm going off on a bit of a tangent, which I generally do. If you use PGP encryption and various other encryption technologies, you can actually encrypt and get one output payload that is encrypted with multiple keys. And then any of the private keys associated with the public keys used to create that one payload can decrypt that one payload. The downside to that, and I've got a screenshot for that too, is they are massive. So not ideal. But anyway, let's continue. So we can come down here and see this third message was sent through. And if we prettify that, we'll see sender 3 sent it to 3 recipients. There's the encrypted version for Alice, the encrypted version for Bob, and the encrypted version for Charlie. Now, as long as you've got one of those 3 private keys, you can decrypt this message, because one of those 3 will decrypt for you. Does that make sense? Probably. Yes, the public keys are for decrypting. Encrypting, the private keys are for decrypting. So these have all been encrypted using the 3 public keys. So as long as you have a private key associated with one of those public keys, because remember you generate the private key first, and then you generate a public key from that. So as long as you've got a private key that was used to generate any of the public keys used to encrypt this, then you can decrypt one of those messages, which is all you need. The n-1 remaining messages, you will not be able to decrypt, and that's by design.
Another question.
Yes.
This is my understanding.
Mm-hmm.
Private key doesn't leave your device.
Private key never leaves your device, hence the name.
How Charlie will have, let's say Alice used her own keys to encrypt.
Yep.
And then how Charlie's going to have that private key. So Charlie should use his own private key.
So the question is, if Charlie has a public-private key, how does Charlie then get somebody else's private key to decrypt their message? You don't want them to. So in our case, if you and I were chatting, you would never get my private key. But the messages would be encrypted once for me, once for you. You can always decrypt the one that your private key was used, the public key was used to encrypt it. You never need my private key. I only need my private key to decrypt the messages that are intended for me, which be encrypted using my public key, which I've shared far and wide. Or in this case, just via a server. At the back.
How would you handle, like, just say, like a restored on a device and a private key you don't want to go across devices kind of thing?
Say that again, sorry? How would you?
It's like an app on a device, and it's got you generate the private key, and then you get another device, and you download the app again, you get a new private key. How would you restore?
I have a slide for you coming up later. The question was basically about transferring from one device to another. So, yes, we'll come to that. All right. Cool. End-to-end encrypted chat app. So, what do we have here? We've got Alice sending a message. They're both receiving the message now from the server using the keys to decrypt. But what if you want to add a third person? So we showed what happens when we added Charlie to the conversation. To start with, the message came in and Charlie was unable to decrypt that message. So what we want to do now is the multi-recipient chat app, which we've already seen the demo for. So how this works is that a message gets gets generated in a machine, and then just the pictorial version of the hand-wavy version I just gave you, grab all of the public keys from the server, and then use those public keys to generate, there you go, bit of code, go through each member of the group, and for each of those members, encrypt the message for that member using their public key, using the sender's private key. Again, private key never leaves the device. That then converts into 3 messages, one for each recipient. Those 3 messages then get saved onto the server, which then get spread out to every member. And in fact, if there were multiple people using the same app but not part of this group, potentially they could also receive these, and that will be fine because their private key will not decrypt any of them. So you can have a system, again, for anonymous purposes, anonymization purposes, if you can have all of your users get all of the messages, it's much harder to work out which messages were meant for whom. And we'll talk a little bit about metadata, traffic analysis, all of the pitfalls later on. So yeah, they use their own personal private keys to decrypt the message, and then they can read it. So that was the demo I just gave you, jumping ahead of myself. It's unusual. All right, so we have a group chat here between all the people, and now we have a private chat between just Alice and Bob, so we've seen that in effect, and we could have used the group chat example before had we not added Charlie to the Alice and Bob chat. Could also have another private chat between these people down here. The issue we now have is, say for example, there is a mechanism by which a private key can be intercepted. And this could be a rootkit attack on your device. It could be handing it over to a border official. Let's not go into that one too much. There are various reasons why your private key could be intercepted somehow. So the problem is, let's say, for example, Bob's private key is intercepted. Then suddenly the private chat between him and Alice is compromised. Because using that one key, you can decrypt all of the messages in that chat. Because remember, only one of the messages in each of the payloads in each of the messages needs to be decryptable. But the problem is, you can also access everything in the group chat, because again, that one key can decrypt all the messages in there. The private chat between Alice and Charlie, still safe. Unless Alice's key is compromised. And Alice here is like the linchpin of the entire organization. She's the CEO. She's in every single group chat, which means if you get that key, you can access every chat that she's in, which is probably every chat. So what can we do to mitigate this kind of situation, or at least the extent to which this kind of situation can affect you? So let's build an end-to-end encrypted multi-recipient chat app with ephemeral keys. Has anybody used ephemeral keys? Anybody know what ephemeral means? I remember the first time I heard it, I'm like, is that like a biological term? I'm not sure. Ephemeral is basically, or an ephemeral key is basically a short-lived key that you use for a specific purpose. So we're still going to keep our per-device public-private keys. That kind of infers the identity of the device. But now we're going to generate a new ephemeral key for each conversation. And in fact, you can then also, through key rotation, and here's where my slides are going to go completely out of whack, because again, I'm taking a tangent. You can also rotate those keys based on time or even number of messages. So there's various ways you can keep yourself more secure. This is going to create what is referred to as perfect forward secrecy, in which if you get a key, you can decrypt every message after that point, but you can't decrypt messages that came before that time. If that makes sense. So how does this work? We are going to keep these as long life keys. So I've moved them up to the top. Meanwhile, down here, we've got this private chat between these two. So when the chat starts, we're going to create a new key pair for this conversation. So each of them is going to create a key pair, the ephemeral key pair, for this conversation only. Then there's a bit about ephemeral keys. So essentially, you can see that we're just using generate key pair. It's a standard key pair again. But you can add other things to it, like we want it to expire at the end of the session, or after a certain amount of time, or after a certain number of messages. So this is very short-lived. The idea is that if you lose them, it's not the end of the world. It doesn't mean you can't decrypt your messages anymore. But any other conversations are going to be secure if you lose these. So the public keys are sent to the server, and the server then remembers these, okay, the conversation between these two here, these are the keys for that conversation. Meanwhile, the public keys, I'm getting it wrong again, public keys down at the bottom there. The private keys stay on the device. But again, this is the private key for the blue conversation. Meanwhile, we have a group chat, that's the green conversation, and each of them is going to create another ephemeral public-private key pair for this conversation. We then store those public keys on the server, and the server remembers, okay, these are the keys for this conversation. All those 5 keys are totally different. None of them being reused, and none of them are the same as the identity key pairs that we had originally. So we've now got 1, 2, 3, 4, 5, 6, 7, 8 different key pairs there for 2 conversations and 3 people. But it's going to give us added security. So we store the private keys locally for that conversation. And we'll see that Charlie's only got 1 because Charlie's a member of the green conversation, as are the other 2. The other 2 also have the blue conversation private key pair, or private key. You'll note that I haven't shown they keep the public key. Technically, they don't really need it anymore unless they want to be able to distribute it again. It's probably a good idea to hold on to it. But for the sake of making this friendlier on your eyes, the server really needs to know about the public keys. Your device needs to know about the private key. So now we send a message to Bob. We grab the keys for conversation blue, We then encrypt that for conversation blue. We'll see there's only 2 payloads here because there are 2 recipients. There were 2 public keys. That then gets saved to the server, gets distributed to everybody. Bob can use his private key for conversation blue and decrypt it. Charlie doesn't have one, so can't decrypt it. So now anybody monitoring the data going in and out of the server doesn't really know who was the recipient because everybody requested it, but only the people for whom that message was intended can decrypt it. So this brings me to the last demo, and then we've got a whole lot of... I've got some math for you as well at some point. It's fun. All right. So we've got Alice and Bob. Alice already has a public-private key pair for the identity. We created that already. So now we're going to create an ephemeral key pair for this conversation. And generating, there we go. And now if I say hello again, we'll see that it's encrypted. I've got a slightly different icon there. So this is the ephemeral key pair being used, whereas the messages above are still being decrypted. They were created using the primary key pair that Alice originally generated. If Bob goes into the conversation now, then he's going to need to generate his ephemeral key pair for this conversation. But of course, because they didn't exist when Alice sent the first message, he can't decrypt it. So again, not intended for you. Still confused, he adds a second question mark. And Alice is like, oh, where have you been all my life? What? So now Bob is able to read these messages. Now what I'm going to do is I'm going to just hover over here. We've got, it's not going to show me this time. Let's open up the admin panel again. We've now got some conversation or ephemeral key pairs down here. Alice has a key pair for conversation 1. Bob has a key pair for conversation 1. Charlie and Eve have no key pairs. So this was generated at 4:15 and 59 seconds, which means that by now, I think it's probably expired because I've given them a 1-minute expiry. So now if we get Bob to come back in here and say, hi, we should see, if I actually hit enter. There we go. So we just saw this one here went to expired in red. It's a bit small, but that says expired. And a new ephemeral key pair was generated for Bob. So now if this key gets exposed, anything encrypted with this key is no longer readable. So now we've got that historical safety.
So was that created by the server or at the device?
The device. So the server can know whether or not it's expired, but the device is where the keys are generated still. Yeah.
So basically Bob's device will generate the second ephemeral key, publish that to a server. The previous one had an expiry time frame.
Yep.
And then the server knows I've got 2 for Bob. The active one is the one.
So the server at this point only needs the last one, because the server needs to be able to tell the next person who's sending Bob a message which public key to use. The one that is expired is useless, so the server doesn't need to know about that anymore. So what happens at this point when the new ephemeral key gets generated is the device is going to go to the server and say, replace Bob's public key with this one.
So you only keep 1 at a time.
The server only keeps 1. You only ever... Now, in this case, we can see that Alice also received the message. If I had gone back a screen so Alice wasn't actually in the conversation, then her ephemeral key would have expired. It would not have sent a new public key to the server, so then Bob would have encrypted it with her old key, because the server wouldn't have a new one yet. So what Alice's device is doing at this point is, we're going to have a look at her keys. You can see there's still only 1 there and it's expired, which means that because it was encrypted using her old key, she was able to still decrypt this. As soon as she generates a new one, it would use the new public key. Now at this point, and again I've got a slide for this, because why not just jump ahead? At this point you've got a choice. On the device, do you keep all of your old private keys so you can decrypt historical messages? Or do you delete them for security reasons because you don't want them to be exposed? And if somebody gets hold of your device, then technically they can probably try and get it out somehow, depending on how you store them. And you can store them in like the vaults that you get on devices nowadays. There are various ways that you can secure that, but there's no 100% foolproof way of protecting the private keys if somebody has access, physical access to your device, or even in some cases, remote access to your device. So you might want to choose to remove those old keys from the devices as well, But at that point, you have to remember that anything that was encrypted with the public key for those private keys can't be decrypted anymore. Now, if you're writing an app like Snapchat, that's probably okay. If you're writing an app for a government to have conversations about strategy and tactics, then you probably want to enforce the retention of those private keys. There was a hand. I got distracted.
No, you answered the question.
Excellent.
Hold on to all the keys if you wanted to.
You're welcome. All right. That's the end of the demos, and I have 20 minutes.
So,
I think it'll be fine.
if you wanted to go through the history of your chat,
Yes.
say, go on holidays, come back, back to my job next month, and then I will go through the history. Then I would have to keep all the keys, unless I decrypted all those messages and save them unencrypted in my device.
Yes, you could decrypt all the messages and save them unencrypted on your phone. But if you want a secure chat app and you're worried about what happens if somebody gets physical access to your phone, I would prefer them to have to try and get the private key out of my phone and then decrypt the messages rather than just have access to the unencrypted data. If in your case, and again, like I say, this is a chat app and it maps analogously almost to probably most business problems. If your business problem is satisfied by, it came to me encrypted, I decrypted and I store it decrypted, sure, do that. You have to weigh up the cost and complexity of encryption and keeping it encrypted at rest on the device versus the actual business benefit of doing that. So if in your situation, storing it locally decrypted is fine, do it. It's much easier. Also means you're going to have fewer problems with backup restoration and all of those kind of things if you need to get access to that data in the future.
So, I mean, you could have another key pair to store them encrypted and...
You could have another key pair on your machine, but at this point now what you're doing is you're creating obfuscation. Because if you've got a public-private key pair and you've got encrypted data and you decrypt it and re-encrypt it with another public-private key pair that's still on your phone, it's the same problem. You just have more public-private key pairs.
Yeah, but if you keep it in your hardware manager, for example.
Why not keep the first two in your hardware manager?
Yeah, why not?
All right. We added Charlie to the conversation. So historical message re-encryption. So we saw that Charlie wasn't able to read the old messages. What if we wanted a situation where you could do that? What if you had encrypted data and you add somebody into the system? Maybe it's, I don't know, a drive of documents, and they need to access these documents that have been encrypted. How can they get access to documents that have never been encrypted with their key pair because they never had one? Right? So what we're going to do is Charlie's going to join the chat, going to create a public-private key pair for the blue conversation. Going to send those to the server, and the server's going to go, okay, cool, new public key for blue. I'm going to store that here. And now Charlie also has a private key for blue. But of course, none of the messages were encrypted with those keys. So what happens now? Bob can grab all of the keys, the public keys now, including the new one that Charlie just added, is able to take the message that he's already decrypted. Now, at the moment, it's in memory on his device, but he could also go to the server and say, hey, give me all of the messages for this chat since the beginning of time. Can now use these 3 public keys to re-encrypt them all and then send those back to the server. And then next time Charlie makes a request for the messages, it gets all the messages, but now the 3 versions, one for Alice, one for Bob, one for Charlie. And now Charlie can also decrypt a historical message with a key that was generated after the message was sent, because we re-encrypted it. It's a laborious process, but it's fairly straightforward. All right, so let's talk about key rotation. All right, that's enough of that one. So key rotation, we kind of spoken about this already. We had a situation where we had blue chat for 2 people, green chat for 3 people. Each had their keys. What's going to happen at some point is the top one there is going to expire. And we saw that expiration happen in the demo. So now what's going to have to happen is that Bob's going to create a new key pair and then update that in the server. You can probably just mildly make out that server key also went grey. So Bob creates a new key pair and sends that to the server. Meanwhile, we saw Charlie join the conversation. So Charlie also now has a blue key pair. Inaccurately, I had the wrong number of keys in the blue square on the previous 2 slides, but ignore that. We'll just smoothly sail over that like it never happened. So now we've got this situation where all the time we're going through time, in this case, or maybe it's a number of messages, and these keys keep expiring. And we've spoken about what happens when keys expire, what do we do with them? So we get to a result where we've got a whole lot of historical stuff. And now if we look at one of the messages on the server, it could actually be that they're encrypted with different keys from different times. And the reason for that is Charlie joined late. Therefore, Charlie might only have 3 keys, the others have 4 keys. So each message will be associated with a key pair. Now, this is where we need to choose what are we actually going to do. The active key pairs, the ones that we're currently encrypting stuff with and decrypting stuff with in our app, for Bob and Alice is not going to be able to decrypt that. So, private key retention questions. Do you want access to historical data? That's the first thing you're going to answer. If you don't need access to historical data, if you're doing Snapchat or, I don't know, let's drug muling conversation chat, sure, let's go with that. You don't want access to historical data. What is the security impact of losing this information? And again, this speaks a little bit to the GDPR question, like, do you have to hold on to data for certain reasons? Medical regulation requires that you hold on to information, typically for most countries, 7 years. GDPR has a right to be forgotten. So how do you balance those things up? So these are questions you have to ask yourself. What are the regulations that affect your system, your industry, your country? What do your business users want out of it? Do they value privacy and perhaps losing information over, I need to, under no circumstances, ever lose this data? Compliance and legal requirements, I kind of bumbled into that one already as well. And operational complexity. Encrypting stuff is operationally complex. And especially when you start looking at the public-private key stuff, that becomes CPU intensive. Somebody already mentioned exponential data growth, and we'll cover that in a second too. Is it worth your time to add the operational complexity to your application? Or can you get away with symmetric encryption? Or can you get away with storing things decrypted on your machine after the fact? So these are questions you have to answer yourself, which will help you work out what kind of key rotation mechanism you need. Resource constraints, I mentioned CPU and like intensive kind of goes together. So the question now is, let's move all of these over here. We've got historical keys, which could decrypt that if you want. And in this case, your app's going to have to be able to be aware of that as well. Do you keep all your keys in the same memory space and you just cycle through them all until you can decrypt it? That, again, is computationally very expensive. Or do you have some kind of mechanism that allows you to take those keys and put them into cold storage almost in a software development sense? And then if the primary key doesn't work, then you have a way of doing a look at which key was used. So there are various ways of doing it. Or do you just forget them, which is so much easier? But your users are not going to be happy when the messages disappear. So again, pros and cons, have to weigh them up. Single-user multi-device. So this is where some of the questions were coming onto on transferring keys, but yes.
The key rotation happening automatically?
No, you would have to code that. So in my case, I created an ephemeral key pair, and they had a 1-minute expiry. So then when a message tried to be sent, the app would say, well, I don't have a key pair, so I'll generate a new one. Yeah. So single user, multiple devices. So these keys I've been associating with the people. They're actually associated with the devices. So let's move the identity keys into the device. We're also going to move the conversation keys in per device. So they're all kind of self-contained there. And now let's say everybody wants to use their phone as well. So how do we get these phones into the system? Well, same kind of thing. We can generate a public-private key pair for the phone. We can generate conversation key pairs for each phone. We can share those keys with the server. So the server now has an additional key to encrypt things with. And now, when you send a message on your laptop, your phone will show the same message. Does that look right? Something wrong with that one? I think we prefer it to look like that. But how do we know that it's the same device? Like, Alice added a laptop, Bob added a laptop. Why wouldn't they be the same user? So how do we know the same user is using multiple devices? And this is where the question of how do you transfer keys, or do you even transfer keys, comes in. So let's have a look at how we link devices. And we're actually going to have, in this case, still each device is a separate client from the point of view of the server and the application. But what we're going to do is we're going to connect these devices so they have a shared identity. That identity is something we can transfer between them without leaking any secrets. And this bit is fun, I promise. So we've got a public-private key pair for the identity. These are all long-lived. We're now going to generate another ephemeral key pair. This is not for, I mean, it is for a conversation, but it's a very short-lived conversation. So we're going to generate a public-private key pair that we're going to use just for the purposes of this device linking process. And we're also going to generate some information, a connection info string. Where can my phone connect to start communicating with a laptop? Got a provisioning request. Here's a unique string of some sort to verify that the request that's coming in is because it's to this device. And you've seen similar things. If you try and log into like a Google Chrome on your TV, you'll get a code and they've got a match. So that's kind of like a provisioning request. It's a randomly generated human readable string. And then we've got a temporary key. That's the temporary key that we just generated, the ephemeral key pair. So we're going to provide that key to the device. And the way we're going to do that is we're going to turn that into a QR code. We need some way of transferring it from one system to another without going through a network that can be tampered or interfered with. Again, when you're trying to connect something to your TV, you see something on the screen, you scan something on the screen, it's not going via a network request. You could do this via NFC, you could do it via a Bluetooth connection, I guess, in some way. But you'll often see the barcode, the QR code option. So then you get your phone, you generate a key pair for your phone, and then scan the QR code, and now the phone has the connection string, the provision request, and the temporary key. So the first thing it does, it says, okay, let's use that connection information to make a connection to the laptop. This is usually done via a WebSocket of some sort. So there's now a connection between the two. It's then going to take the private key of the device generated, and it's going to add that to the provision request, and then it's going to use the temporary key to encrypt the entire bundle. So now we have an encrypted payload, which is the request, which again is our verification that it's the correct request, and the device's private key, a public key, and it's been encrypted with the ephemeral public key from the laptop. Right? There's a lot of keys. There's a lot of keys going on. So that encrypted provision request can basically only be decrypted by the, can I use this thing? There we go. It's really slow, but this private key there is the only thing that can decrypt that encrypted provisioning request. And that request, once decrypted, let's just send it over. So we're going to send that over via the connection. We're then going to use that private key to decrypt it. It's verified as decrypted, and now we get the provisioning request out and also the public key from the device. Provisioning request is just matched. Like, if the provisioning request I get is the same I sent, then this is the provisioning cycle that I started. So now we've got the public key of the device, the new device. So we can now generate an identity token of some sort. This could be a JSON web token, it could just be an email address, or even just a user ID. It could just be one number. And we use the public key that got transferred over just now. We use that key to encrypt the identity and send it back to the phone. The phone can then use its private key to decrypt it, and it now has a JSON web token or some kind of verifiable information that has shared the identity between the two. So now when it comes to sending messages, it'll say that they're both from the same device, not because they're encrypted with the same key or decrypted with the same key, but because the message sender is the same as the user ID that the device knows it is representing. So my user ID might be ben@dechrai.com. Therefore, if the message was intended or sent by a device that identifies as ben@dechrai.com, then I know that I sent it. So now all of my devices can say this was sent by me and represented in a way that says this is my message as opposed to somebody in the group chat. Does that make sense?
Wouldn't that be the same as logging into that device and authenticating through SSO or whatever the case might be?
If you want to set up an identity server, you could do it that way too. But it would be the same outcome. The thing now is that you're delegating identity to a third party, which if you want to do that, that's totally fine. But in a lot of cases, especially in chat apps, and again, if this doesn't work for your particular use case, then don't do it that way. But most chat apps, when you start up, you don't actually have to create an account. You might have to put your phone number in and get a verification code, but there's no real system that has identity or a login mechanism. It's not a transfer, it's basically a way of communicating securely between two devices to share information outside of any known authorization. So they don't know who I am, but I'm able to get two devices of the same software to talk to each other in a secure way that even if somebody manages to sniff the network traffic between the two, I'm able to transfer that identity information over without having to rely on a third party. So 5 minutes? All right, let's see how much we can rush through this part. I'm loving the questions. Wasn't anticipating them, but I really love the fact there's so much engagement, so bear with me as we try and get through. I think the rest of this is probably going to be less. Actually, no, there's some maths coming up. This will be fun. Okay, so scalability. Somebody already talked about this is going to explode, especially when you've got a message encrypted, or a single message encrypted for 3 people means 3 messages. So if you send a message from one device to all the others, there's like 7 messages already in the system. Then somebody else sends a message, that's 4 more, so now we've got 11 messages stored in the system for 2 actual messages that were sent. And then this device wants to send another message, but it's like 2 minutes later and the ephemeral keys died, so those have died. Now we've got other messages that are encrypted with a different key, so now we've got multiple keys, and we've got 15 messages just for 3 messages that have been sent within this network of devices. So you can see the amount of data stored is growing exponentially. And if you consider the way that public-private key encryption works with OpenP or Pretty Good Privacy or the other one, GNU PG, all kind of same implementations, that is a message encrypted for 2 people. And I believe it says something like, hi. So, what we're going to do is use symmetric encryption. And at this point, you're like, what's going on? You just told us that wasn't any good. That's weak. Yes, it is weak. But it is faster, easier, and it'll give you a smaller ciphertext. So the stuff that I was copying and pasting and showing you the JSON, that also said hi, but it was so much smaller because I was actually using symmetric encryption in there on top of asymmetric encryption. And this bit is fun. The thing that we want to be able to do is get around the issue of key compromise. We want to get rid of the issue that symmetric key encryption is less secure because of the fact that there's one key. You could have a key per conversation, but it's still the same key for encrypting and decrypting. And the whole point of a shared key is everybody knows it. So how do you transmit that between systems? And we've already seen one way of 2 systems communicating and sharing information, but this one's more fun. We also want to get away from the issue of having to encrypt server-side. So we're going to use symmetric encryption, but in the device, as well as asymmetric encryption. So we're going to use the Diffie-Hellman key exchange. Anybody know the Diffie-Hellman key exchange? This one's fun. So Alice and Bob want to come up with a shared key so they can symmetrically encrypt their messages. So they could just go, I'm going to use blue as the password. But now anybody in this room heard that blue is now the password. So how do we come up with a shared key without actually telling each other the shared key? So they start off by just thinking of a number. You can play along depending on how good the maths in your head is. So Alice goes, I pick 6. And Bob says, I'm going to go with 5. It's coincidence they're 1 apart. It could be like 4.5 billion and 3.8. Actually, I don't know if it can be decimals. But anyway, so they imagine a number. Then they also shout a number at each other. Alice says, 7. Bob says, shit, 23. And then, because it's software, actually, like we make some kind of determination of what order to use them in. So let's use the lowest one on the left and the highest one on the right. And Alice says, okay, so I'm going to take the 7 that I shouted out, and then I'm going to raise that to the power of the number that's in my head that nobody knows. And then I'm going to get the modulus of the number that Bob shouted out because that was the higher number. And everyone's like, what the fuck is she doing? And she goes, okay, I've got a 4. So she goes, 4. And he says, keep it down. And Bob goes, okay, I'm going to take the 7 that Alice shouted out, modded by the 5 that I imagined, then raise it by the 5, and then mod by the 23 that I shouted out. I'm going to get 17. And Bob goes, 17. But everybody heard, because we're all nosy. And then Alice says, okay, cool. So I'm now going to take that 6 mod 3 raise power thing, but instead of the 7 that Bob told me, I'm now going to use the 17 that Bob told me. I'm going to get a 12. And then Bob goes, this is crazy. And he says, okay, I'll do the same. So he then takes the Alice it out and does the raise to the 5 mod 23, and he also gets 12. I reckon we can use that as a shared key. For some reason, that works every time. I think it's pure magic. I think it's pure magic. So we now have a shared secret. So we used our public-private keys Actually, no, in that case, there wasn't any public-private keys. They would probably use the public-private key for communicating the short numbers, just to keep it a bit more safe, but you don't have to. But they came up with a shared secret, and now they're able to use symmetric encryption using that shared secret in order to share information between themselves because they individually derived the same secret. It still blows my mind. So Alice says hi, grabs the super secret of 12, uses that as a key to encrypt the data, sends it to the server. So now, even though we're using symmetric encryption, it's happening on the device, and the server still has no idea what the original was. It's still being transmitted in encrypted version. Bob then uses the same key that he magically derived, because he's a genius, and comes up with the original message, hi. Isn't that cool? Thank you. I mean, I didn't come up with it. But
didn't one of those numbers needed to be prime number?
Usually you go with a prime. You'd want to go with a hard-to-guess number. I mean, if everybody used numbers less than 25, you could build a rainbow table of all the possible keys. So yes, you would use sufficiently large prime numbers to make it really hard to guess what those original starting values were, but the math still holds up. Also, the secret would be way bigger than 12. Am I at time? I'm getting a little nod from the corner. All right, so let's just rush through these. We've got 7 entire messages here between these 3 people. And if we look at the network graph, we've basically got a conversation. Charlie says, I missed that. And Anna says, now you'll get it. And then Charlie says, thanks. And Charlie says, hey. And then Anna says, yeah. And Charlie says, where's Bob? And Bob says, I'm here. 7 messages between 3 people, 21 messages. Grows quickly. So that's what the payload looks like of that conversation in the demo app, because we're using symmetric encryption to encrypt the data, which is a lot smaller payload. It's also a lot faster and easier on the CPU. Compare that with what we had originally. That's basically one message. You can see there user ID 1, 2, and 3 on the left-hand side. So that's one message. That's what it looks like. And compare that to what we had originally with one message between 2 people. This is already a lot more compact, and when you try and decrypt it, it's going to be much easier on your system, less operationally overheadness. All right, metadata attacks. I'll rush through this. I realize we're over. I appreciate you for hanging around, but it won't take long. So we've got a whole load of users here in the system, and metadata can give away a lot of information. You might notice those 2 over there communicate each Sunday at 10 p.m. We've got a group of 14 out of the entire 18 people in the organization just went into a group chat immediately like that. They didn't get added one by one. We've got this one guy over here that sends a large message to an external recipient every Friday at 4:05, but the recipient never replies. We've got a person in the organization who's a member of 70% of the chats, but hardly ever contributes to them. And then we've got a group of 7 that has 3 active members, 2 occasional participants, and 2 silent observers. This is all the information we can get from metadata by looking at how the messages get sent, who pulls those messages down. You can't see the message, but metadata gives away so much. And now we can use our imaginations to try and work out what's actually going on. So those 2 are probably the co-founders, right? They're chatting every Sunday night. What are we going to be doing for the week? Who do we need to fire? You know, the typical questions. The shit really hit the fan when this group was created. I don't know what happened. I'd be very excited to be a fly on the wall. This guy here, why is he sending data out every single week to some unknown external recipient who never replies? We think this person is probably going to be the CTO rather than CEO because they are a part of 70% of the conversation, so maybe they're keeping more of an eye on it than the CEO would. Maybe. So what's happening in this one, though? We think that's the CTO, so that's probably the CEO. We think this one here might be a spy. They're talking a lot. They're the active participants. There's 2 that hardly contribute much. Maybe the manager's been pulled in because they're like, what are you doing, dude? And maybe the CFO because he's leaking financial data. So which means we've got HR and legal in there as well. Suddenly we've got a very good inference. I totally made it up. But we've got a very good inference of what each of these devices, who they belong to. So metadata will give away information, not the content, but patterns. So some things we can do. Actually, no. These aren't things we can do. These are other things we might notice. Message size. If the messages are usually very short, they're probably yes/no kind of answers. If they're the same message size at the same time of day, maybe it's a status report. So you can now start inferring what the content of the message is as well. Perhaps. It's very vague, but the data's there to try and work it out. Message frequency. Message frequency between finance team members increases by 300%. Maybe this is a financial reporting season. Communication patterns. If suddenly communication used to be hierarchical, but now there's a graph, something different is happening, you can detect that something in the organization has changed. You might not know what, but you're still inferring things. So metadata gives away a little bit of stuff that maybe we don't want. So what can we do to protect ourselves against this? First thing we can do for message size is we can standardize to fixed blocks. Make sure that every message that gets stored is a multiple of 512 bytes, for example. That way it's harder to infer what's actually in there. For working out who's communicating with who, create decoy traffic. Just make up some public-private key pairs, generate a random string, encrypt it, store it in the database, and anybody looking at the traffic is now like, well, I wonder who's communicating over there. Nobody will ever be able to decrypt it because you just forget the public-private key pair straight away, but now you've got noise in the machine, and that's really useful. Retrieve all the messages. I mentioned this before. If everybody receives the messages but it can only decrypt the messages intended for them, then it's harder to do traffic analysis on who's receiving which messages. If everybody gets everything, it's really hard to work out who it's for. So, in summary, I'll go through this very quickly because I appreciate your time. We've gone through why we need encryption, the evolution of secure messaging from just a plain text all the way through to super encrypted. We had a look at key features like multi-recipient encryption, how ephemeral keys are going to help you with perfect forward secrecy, and how we re-encrypt messages. We've looked at implementation challenges. We have gone through some of the core technologies like Diffie-Hellman. That was a really fun one. I like that one. We've gone beyond encryption and looked at communication patterns, traffic analysis, all of those kind of things. These are all things that I hope you will at least be able to take away and look into more if this is something you're looking to implement within the products you're working on. I would like to thank you for your time. I've gone a little bit over. I'm sure you will forgive me. If not, come and complain to me outside. I have no time for questions. Thank you. Have a great rest of your day.